Let me start. So my name is Alexander Kirnasov. I'm heading a quantitative development in Znamenka Capital. That it is a high-frequency trading company based in Moscow, and also I hold PhD degree in mathematics from Moscow State University. And today I'm going to present a paper called Quantum Reinforcement Learning for High-Frequency Trading. Before we start, let me emphasize 2 points. So first of all, because we don't have too much time, I will only focus on some key highlights of the paper. If you want to know some more details, please refer to the paper itself and to the GitHub implementation in Python, and the reference to the GitHub is also provided in paper. Also, I would like to mention this is mostly research work, even though in the end I will present the results of the backtesting. But still, for example, in our company, we are not yet implementing it because there is a common problem with all deep learning approaches in finance specifically. Its requirements for huge amounts of data and huge resources like GPUs and so on. But potentially this is possible in some other companies, for instance, for big market makers or something like this. Okay, so let's start with presentation. So first of all, I would like to mention which types of machine learning broadly exist and which of them are used in finance and specifically in high-frequency trading area. Most often we could find papers related to supervised learning applications, and basically it's a classification and regression. Most often you can find papers devoted to mid-price prediction in a few ticks, like 10 or 20 or 100 ticks. On the other extreme, there is unsupervised learning, when primary goal is to find some features in the data set, and most of the time it is used to cluster the features which can help to predict some properties in finance. So, for example, in the same problem of mid-price movement. And finally, in between of those two classes, there is reinforcement learning. Originally, it is used in control, in robotics, and autopilots. You may also recall the papers from DeepMind company related to applications in various games such as chess, Go, video games, and so on. And the main difference and the feature of reinforcement learning, which is, I believe, very attractive for financial applications, is that agent does not have predefined plan of his actions, and he's trying to define the optimal planning on the go while he's investigating the environment, in our case, the financial markets. Then it builds automatically the strategies, the optimal strategies itself. And that's, I think, the key advantage of reinforcement learning compared to supervised learning. So let's briefly review the reinforcement learning itself. So there are two main concepts in RL. It's environment and agent. So agent can observe the states of environment, and based on the state and his policy, he is choosing the action which he thinks will optimize his rewards. So on every action, agent receives some reward from environment, and his goal is to maximize total reward. So he wants to make a policy that does this. So formally, there is a state space. It's a set of all possible states observable for the agent. There is also action space. These are all actions that agent can take. There is a transition function, which is a map from the pairs of current state and action is mapped to the next state, and a reward is a mapping from a pair of state and action to the reward. For financial markets, reward can be transparent. It's just the profit and loss, for instance, in money, in actual money. And of course, the agent wants to optimize not just immediate reward, it wants to optimize his total reward. So he may have some not optimal, not maximal reward right now, but he may take some actions which will lead to maximal reward in the future. So basically, he is trying to optimize the sum of all rewards. And we also add the discount factor in the summation to potentially consider as larger horizons of summation as possible. So formally, in mathematical form, we want to find a policy pi, which is maximizing the Jacobian, and Jacobian is defined in the mean of all global rewards through all the paths which agent can take in the environment. And when we consider this mathematical formulation, usually the two concepts are introduced. It's a state value and a Q function. State value is a mean global reward that the agent can receive if he's starting from current state S. And the Q function is action-specific value. It depends on current state and an action. And it's a mean reward that he can receive starting from current state and taking action A. So when the state space is not large, and that was original algorithm how to solve this problem, we can just iterate through the episodes, so-called episodes, which are tuples of steps, current state, action, next state, and reward. And we can iteratively update the value function, the Q of S and A, applying the Bellman principle. The Bellman principle is quite simple. So we basically want to take maximum of immediate reward plus maximum value of the next state. Again, as I said in the beginning, because we are limited in time, I'm just briefly describing the concepts, so highlight the principles. But if we consider actual states, actual environment, like in financial markets, of course, the number of states is huge, and we cannot just simply iterate through this algorithm. And that's when the deep Q-learning appears. It's an approximation of Q function, and we basically target to build the deep learning model that approximate the Q function. So as an input of neural network, we have the environment state and action, and an output is the Q value of this pair. And our loss function is based on the same Bellman principle as I just mentioned before. So that's how this problem is most often solved in practice, and this algorithm is called DQN. Although that's the not only approach, there are some other, but DQN is quite often used. So now let me turn to brief description of what high-frequency trading is. So basically, it's based on idea to perform a lot of micro trades, each yielding some small returns, but together, in the end of the day, resulting in large positive return. And it, in fact, can be considered as automation of so-called scalping strategy, which is reaching the speed limits to microseconds and below microseconds. So now let's discuss what can be used to quantify the HFT. And the two most valuable sources of quantified data that can be used are limit order book dynamics and trade history. So let me briefly describe what is limit order book. Here on the screen, you may see example. Basically, limit order book aggregates the intents of market participants. It is composed of two parts. On the seller's part, there is number of price layers, price levels, and on each price level, there is an aggregated quantity which can be offered by sellers on that price level. And symmetrical is for buying side. So once again, this is aggregated information about intentions of all market participants, and that's why itself limit order book and how it changes in the time is quite important information for automated trading. Now let's describe trade history. It's actually just a list of last committed, let's say, end trades. And unlike limit order book, which is just an intentions of market participant, trades are actual deals, like realized intentions of market participants, and that's why they even have some more information sometimes than the information from limit order book. So that's another element of the data that we can quantify and use. Now let me also mention what are the conceptual differences of quantum RL from previous approaches. Actually, applications of reinforcement learning in finance are not new, especially in market making. They're relatively new for directional trading, which I'm describing here. But the main conceptual difference of quantum RL is that we are not only considering so-called level 2 data, which is the dynamics of limit order books and trades, but also the concept is to consider all individual quantum events that led to formation of this current limit order book. And this is basically called level 3 data. These are all individual limit orders at cancels and market orders, which are actually trades. In our experiments, we did it on Binance. Binance does not provide level 3 data, unlike regular exchanges like traditional exchanges, NICE, and so on. But Binance can provide some reasonable approximation of level 3 data, which is basically the deltas between two successive limit order book states. And essentially, this is aggregated level 3 data based on some frequency, let's say 100 milliseconds. It can be mentioned that in such form, this can be also received from just taking deltas from level 2 data, but in this case, still, it is some improvement to original approaches, which usually consider just level 2 data, because we basically do the feature engineering for better, for providing neural network with better initial data, which is, in this case, deltas between states of order book. Technically, the environment state, so if you recall, the reinforcement learning requires us to define what is the environment state and what are the actions. So let's define the environment state. It's composed of microstructure state and macrostructure state. So microstructure state is represented as a time series of 100 latest updates, which I mentioned is basically the deltas between the successive limit order books, plus 100 latest trades, and plus current limit order book with 10 levels. So updates are represented as tuples: update type, price level absolute, price level relative, size absolute, size delta, and timestamp. And update can be update, delete, or insert. So we can update some level, delete level, or insert new level in the book. And trade is represented as trade price, size, trade direction, and timestamp. And one more difference in this approach, in quantum RL approach, is that we also add a macrostructure state into QRL, which to my knowledge is quite new to such approaches. The idea is that we also add 3 time series of 15-minute, 1 minute, and 1 second price candlesticks. Each time series has length 10. Price candlestick is well known in technical analysis. It's usually represented as a tuple open price, highest price, lowest price, and close price. And finally, we also add 3 pairs, maximal price, minimal price for each time series. This way, the idea is that we supply our agent, the neural network of the agent, with both microstructural information from level 3 data and macrostructural price information from prices on lower frequencies. And now let's define the agent actions. So after the agent's neural network has an input of state and an action, and action can be one of the values none, buy, sell, and close. The neural network provides 4 values for each of these values, and on each the DQN policy is to choose the action which maximizes this value. So the actions can be do nothing, so stay without any other actions, buy, sell, and close. Buy mean in our case, buy 1 minimal BTC USDT perpetual futures contract. Sell means short 1 minimal contract. And close means close accumulated position and complete the episode. And let me briefly describe the architecture which was used to train the model. So as I mentioned, this state is represented by current limit of the book, a series of 100 updates, a series of 100 trades represented in the form that I described before. If also provided by exchange, it can be 100 level 3 data, which are individual orders of market participants, and then 10 candlesticks, 15 minutes, 1 minute, 1 minute, 1 second, 3 min-max values. Limit of the book is processed by 2 linear layers, each from 64 neurons. Each time series is processed by LSTM with different settings. And finally, 3 min-max pairs are processed by another linear layer with 64 neurons. The outputs of all layers are concatenated into a vector of 70 of length 73, and this is processed by another linear layer of 64 neurons, and that provides us the Q values for 4 states that I mentioned before: none, sell, buy, or close. Now I'd like to briefly describe the experiment. As I said, it was done on Binance. So the trading pair was BTC USDT perpetual future contract. The data was collected via WebSocket API with mean update interval about 100 milliseconds. 1 day data was selected for training, and the next day data was selected for testing. I used RTX 3080 GPU. And in the experiment, the taker fee was assumed to be 0.1%. It was actual at the time of experiments, but actually now the situation is even better. The taker fee commission is only 0.05%. So I'd like to report just 2 main graphs as a result. Probably the most interesting. As I mentioned in the beginning, if you are interested in details, please refer to original paper and also to GitHub repository, which is also the link to the repository is given in the paper as well, as long as the training and test data also can be found in repository. This is basically result on the test day, on the second day. so our agent was trained on the previous day data, and now he's trading with this policy, as I described before. And here we can see that after just 3 hours, it was able to reach this quite attractive PNL. And as I mentioned in the beginning, again, this is still research data. So even in our company, which has enough resources which has sufficient technical infrastructure to launch the strategy, but still we don't have such large resources to process a huge amount of data and processes with GPUs and so on. So please mention, I'd like to mention this is just research yet. And finally, another interesting chart is that how how agent is learning. But this is typical situation for actually reinforcement learning experiments. In this chart, we are drawing the average reward for last 100 completed episodes. And as we can see, somewhere between 1 million and 1.5 million steps, the network starts rapidly improving and then stabilizes, and in around 12 hours, it reaches levels which allow to provide such good results on the next training test day. But as I said, this is quite typical situation for reinforcement learning, this spike in ability of the agent somewhere in a short period. And same situation we can observe here. Briefly, I would like to describe about the future plans. It is interesting to consider transformers architecture as advance of LSTM, even though sometimes it is arguable what is better architecture for time series, whether it is transformers or LSTM, but still it is interesting to check transformers because, for instance, for mid-price prediction, you can find in the papers that transformers are performing best at the current time. So the precision quality is maximal for transformers. So that's why it is interesting to also check them for this architecture. Another direction is to apply similar architecture to high frequency market making. As I mentioned here, this trading model is basically directional. It has signals buy or sell, basically, which is directional. And the difference in market making is that it quotes both sides simultaneously. Again, there is a number of models of reinforcement learning for high frequency market making in the literature, but none of them is considering level 3 data, which I think should be used as well. Another approach can be used to apply news analysis. As I said, our state is represented by microstructural state of limit order book, even level 3 data, plus macrostructural state, which is the time series of candlesticks on lower frequencies. And in addition to that, we can also add the news analysis on lower frequency. And for instance, we can use such recent advances in language processes such as ChatGPT and large language models. And another direction is to test this on regular exchanges. Thank you. So